All right, let's dive into something a little surprising today. For all the talk about AI changing the world, conquering games, writing essays,
Yeah.
turns out it's often, well, pretty bad at the kind of real-world stuff you or I deal with. I'm talking about basic logistics,
Uh,
getting things from A to B efficiently,
hmm
scheduling complex operations, making sure everything arrives on time without, wasting resources.
It's a fascinating paradox, really. We see AI doing amazing things in these abstract areas, but uh, the messy, dynamic reality of planning delivery routes or, say, optimizing schedules, that presents some really fundamental challenges.
Absolutely. I mean, imagine you're running a delivery service.
Yeah.
Busy city.
Yeah.
You've got maybe 50 packages to deliver, each with a specific time window someone has to be home then,
Mm-hmm.
and your truck.
Mm.
Limited space.
Right.
And then new orders are popping up constantly,
Huh.
trying to figure out the absolute best way to do all that. Hit the windows, stay under capacity, shortest drive time.
Mm-hmm.
That's where traditional AI, even really powerful computers, they just start to sweat.
And that complexity, that specific kind of challenge, is exactly what we're unpacking today. We've got a source, a really interesting YouTube video transcript, actually. It dives into a new breakthrough from DeepMind that aims to tackle this specific problem head on.
Okay, so our mission for this deep dive then is to figure out why these kinds of puzzles, logistics, scheduling, why they're so tough for computers,
Hmm.
and then understand what DeepMind's new approach actually is, see how it stacked up when they tested it apparently on some pretty brutal scenarios,
Oh, yeah.
and most importantly, what this could ultimately mean for you. Everything from whether your pizza arrives hot
Yeah, right.
to maybe optimizing things like hospital surgeries. Big range.
It's really about giving AI what you might call street smarts for the real world. If they can crack this nut, the implications are just huge.
Okay, so let's start there.
Hmm.
Why is planning routes and scheduling so hard for machines? Especially when you compare it to, like, beating a chess grandmaster.
Well, at their core, these logistics problems are what are called combinatorial problems.
Combinatorial.
Yeah, they involve just a staggering number of possible choices. Think about that 50 house delivery route again. Just swapping 2 stops, then another 2, then maybe moving 1. The number of potential routes explodes incredibly quickly. It's astronomical.
Wow.
And you have to find the optimal choice or something very close to it while following a really strict set of rules or constraints, like those time windows we mentioned, or the truck
I
capacity.
think I've heard the term NP hard thrown around for problems like this.
Exactly. That term does pop up in our source. And it basically means that finding the perfect, absolutely guaranteed best solution, while it can take a computer an impossibly long time as the problem gets bigger, the possibilities just grow way too fast for even the fastest machines to check every single one.
But okay, why can't modern AI handle this?
Yeah.
Neural networks, right? They're amazing at recognizing faces or translating languages. What's different?
That's because neural networks are really designed to find patterns in what we call smooth, continuous data.
Smooth
Right.
data, like images.
Exactly. Like the shades of pixels in an image, or the subtle shifts in sound waves in speech, or the flow of words in text. They work incredibly well with probabilities, approximations, fuzzy stuff. But logistics, that requires rigid all-or-nothing decisions.
Ah.
Did the truck make the delivery at that exact address? Yes or no? Was it within the time window? Yes or no? There's no maybe. These tasks demand clear-cut logic and really strict adherence to rules, which, traditional pattern spotting AI just isn't built for.
Okay, got it. So AI, great at fuzzy patterns, not so good with hard rules.
Yeah.
But what about the other side? Traditional computer methods, the ones specifically designed for planning and handling constraints. Can't they solve this?
They can handle the constraints, yes, they're built precisely for that. But the big drawback is they tend to be incredibly slow, especially when you need answers fast in real time.
Right, like for that dynamic delivery problem.
Exactly. And they often require perfect information right at the start. You have to know all the requests, all the constraints, everything before you even begin calculating. But real-world logistics isn't like that. It's messy, it's dynamic, new requests come in, traffic jams happen, things go wrong. Those traditional solvers, that are just not practical for that kind of fluid environment.
Okay, so we're kind of stuck then. It sounds like AI is fast, but flunks the rules test. And the traditional methods follow the rules, but are way too slow and rigid for the real world.
That's precisely the gap DeepMind was trying to bridge here. They wanted to create an AI system that could approach these problems with the speed and the learning ability of modern AI, but also have that structured, rule-following logic that you absolutely need for planning. Essentially, teach AI to plan like a human expert, but, super fast and at a massive scale.
And the key to their solution, the source called it a smart explorer.
Right, let's stick with that term. It's a good analogy. Forget the really technical jargon for a second. Think of this smart explorer as like a highly intelligent assistant for the AI. It helps the AI navigate this incredibly complex landscape of possible solutions. It's like giving the AI a really sophisticated GPS, but one that can figure out the best route even if the map isn't perfect and, the roads are changing all the time.
So how does this smart explorer actually find a good solution? Does it just guess randomly?
No, not randomly. That's the smart part. Instead of trying to map out every single possibility, which we already said is impossible, the Smart Explorer starts with a potential plan, maybe not a great one initially, and then it intelligently explores nearby options or tweaked options. It makes small changes like swapping 2 deliveries on a route or maybe moving a task to a different time slot, little adjustments.
Okay, but how does it know if a tweak is actually better? Is it just guessing?
It uses built-in clever rules that are inspired directly by the constraints of the problem itself. So if it's a delivery route, the rules check. Does this change save time? Does it cut down the distance driven? Does it still make sure the truck isn't overloaded? Critically, does it keep everything within those required time windows? If a tweak improves things according to these rules, the Explorer is much more likely to sort of accept it and move forward from there.
The source mentioned something about this being inspired by simulated annealing. That sounds physicsy.
It does, yeah, but the analogy they use is quite neat, actually. Simulated annealing comes from metallurgy, the process of slowly cooling metal to align its crystal structure and make it stronger, more stable.
Okay.
So they apply that idea to the AI search process. It means the AI starts out being more open to making bigger changes, exploring more broadly across different types of solutions, kind of like being hot. But over time, as it starts finding better and better solutions, it gradually cools down. It becomes more focused, more likely to accept only small, precise tweaks that really refine the plan. This helps make the final solution robust and highly optimized.
And the really critical part you said is that this smart explorer isn't some separate tool. It's built into the neural network itself.
Precisely. That's the core innovation here. By making this structured, rule-based search process a layer within a learning system like a neural network, the AI can actually learn from its explorations. It starts to see which kinds of tweaks consistently lead to better outcomes for this specific type of problem, and it gets smarter and more efficient at searching over time. It combines the neural network's amazing ability to learn and adapt with the structured logic needed for planning. Best of both worlds, hopefully.
Okay, let's peel back the hood just a little more then. How is this fundamentally different from those older methods, the exact solvers you mentioned earlier, the ones that are too slow?
Right, those old exact solvers, they were really trying to find the single perfect answer, guaranteed optimal. They did this by essentially checking possibilities exhaustively. Like, imagine trying to solve a billion-piece jigsaw puzzle by methodically trying every single piece next to every other piece. You'll get there eventually.
But it takes forever.
Exactly, especially for big, complex problems.
And this new approach is more about smart guesses.
Yeah, that's a good way to put it. It builds on established ideas from computer science called local search heuristics.
Heuristics, like rules of thumb.
Kind of, yeah. Think of them as intelligent shortcuts or smart guesses that can quickly find a very good solution, even if it might not be the absolute mathematically perfect one 100% of the time. The key difference here, the DeepMind twist, is they've made these smart guesses, this local search process, learnable.
Learnable? How does an AI learn from just making a guess?
This is where the term differentiable comes into play. We don't need to get lost in the calculus, but what it means practically is that the AI can actually evaluate how good its search steps, its guesses were. It gets feedback, and it can use that feedback to adjust its own internal workings, to improve its search strategy for the next time. It's a bit like learning by trial and error, but in a highly structured, efficient way that's baked right into the AI's learning process.
Okay, and there was something about a scorecard that helps with this learning, makes it faster.
Yes. The source mentioned Fenchel-Young losses. Again, technical term, but the scorecard analogy captures it well. Imagine you're trying to improve your delivery plan. Even if you only make one small tweak, swap 2 stops, say the system can quickly assess how much closer that specific tweak gets you to a potentially much better plan overall. It doesn't need to calculate a whole new route from scratch to get useful feedback. This scorecard gives immediate signals, which helps the AI learn and train much, much faster and more efficiently. It keeps the learning on track.
Now, when they actually tested this thing, did they just let the AI start from scratch, or did they give it some help?
They tried a few different starting points, which is interesting. They tested starting the AI search from a known good plan, basically,
Yeah.
the best solution found by older, slower methods in previous competitions, a benchmark. They also tried starting it from a plan that was just slightly improved, using one of those quick heuristic guesses, like a rough first draft. And the source definitely notes that starting with a pretty decent plan already helps the AI refine it to near perfection much faster.
Makes sense, right? Less
Yeah.
ground to cover.
Yeah, that makes sense. Okay, so they've got this smart explorer layer. It's inside a neural network. It learns how to search using the scorecard thing. How did it actually do when they threw it at a really tough real-world type problem?
Right, the testing.
Mm-hmm.
They really put it through its paces. They used a challenge problem from a major competition. It's called the Dynamic Vehicle Routing Problem with Time Windows, DVRPTW for short.
Dynamic vehicle routing problem with time windows. Okay, DVRPTW. Sounds intense. What makes that one so tough?
Well, the dynamic part is key. Requests for deliveries keep appearing throughout the day, not all known up front.
Ah, like in real life. Exactly. So you have to constantly update routes and schedules in real time, on the fly, and then you have those strict time windows. You must be at location X between, say, 2 p.m. and 2:15 p.m. No earlier, no later. Plus, you've got vehicle capacity limits. It's basically a constant firefight of real-time planning under serious pressure. The source called it the ultimate logistical nightmare simulation.
Wow, okay. Sounds suitably brutal. How did they set up the actual test runs?
They simulated this dynamic environment, having requests arrive in waves, and significantly, the tests were run on just a single CPU.
Not like a giant supercomputer cluster.
No, which is important for practical application. They used a bunch of different problem scenarios for training the AI and then a separate set for testing it. Some scenarios had up to 100 new requests arriving in each wave. And crucially, they didn't just run each scenario once, they ran each one multiple times, averaging the results over 50 runs. This makes sure the performance they saw wasn't just a fluke, that it was consistent and reliable. Oh, and they used a specific type of neural network called a graph neural network, which is good at understanding relationships like the connections between locations, vehicles, and requests on a map.
All right, moment of truth then. Drum roll, please. How did DeepMind's new shiny method actually compare to the older ways of doing this?
So they compared it against a strong baseline method from the competition, one that used simple perturbation. That basically means adding random small changes to a route and just hoping it gets better. Much less intelligent than the new Smart Explorer.
Gotcha. And the results,
Yeah.
especially the speed. The source mentioned tests at just 1 millisecond. That's crazy fast, faster than blinking.
Yeah, at that lightning speed, 1 millisecond. The new method was remarkably close to a theoretically perfect plan, what they call the anticipative baseline, which unrealistically knows all future requests in advance. The new method was only about 7.8% worse than that impossible perfect score.
Only 7.8% off perfect in 1 millisecond. That's impressive.
And the old method.
The old perturbation method. At 1 millisecond, it was a whopping 65.2% worse than perfect.
Whoa.
Yeah, the source used a great analogy for that gap. It's like the difference between getting your package delivered within the hour versus maybe getting it next week. That huge speed difference is where the real practical value lies for dynamic problems.
That's a massive difference at high speed. Okay, but what if you give them more time, say a full second, 1,000 milliseconds? Does the old method catch up?
So given a full second, the performance gets closer. The new method reached about 5.9% relative cost compared to perfect. The old method actually got slightly better, around 5.5%.
Whoa, so neck and neck on quality if you give them enough time. Pretty much, yeah. But the key takeaway is that the DeepMind approach gets to a very high-quality solution so much faster. For real-world situations where you need quick decisions as things change, that speed makes it miles ahead in terms of usability.
And did starting with a decent plan, that heuristic start, make a difference in the actual test results too?
Absolutely. The source highlighted this specifically. When they started the Smart Explorer from a plan that had already been slightly improved by a simple heuristic, it managed to reach that excellent 5.9% quality level in just 100 milliseconds.
Wow, 10 times faster than needing a full second.
Exactly. It shows that giving the AI even a slightly better starting point really helps it zero in on a great solution much more quickly. It's like giving it a good head start.
They also mentioned tuning something called the temperature. What was that about?
Right, the temperature. Think of it like a knob controlling how adventurous the AI is during its search.
Adventurous.
Yeah, a high temperature means it's more willing to explore radical changes, to jump to potentially very different solutions, even if they look worse initially. More exploration. A lower temperature makes it more cautious. It sticks closer to the current best plan and mostly accepts only small, precise tweaks that offer clear improvements, more exploitation of what it already knows. They found that a temperature setting of around 100 was the sweet spot for refining a plan when it already had a good starting point, like that heuristic start. Lower temperatures helped more when it had to build a good plan from scratch.
Okay. And did they check if this whole Smart Explorer idea works on simpler problems too, not just this monster DVR PTW thing?
They did. They tested it on easier, standard combinatorial optimization tasks, like picking the best combinations of items under certain rules. And apparently, it performed really well there too, quickly finding solutions very close to the known perfect answers. Yeah, and they also found that running multiple smart explorers at the same time in parallel was effective. It was like having a whole team of explorers working on the problem. It significantly sped up finding great solutions without hurting the quality.
And just to be sure, the math behind all this, it's solid. It's not just some clever trick that might break.
The source makes a point of emphasizing that, yes, the method is rock solid mathematically. It comes with convergence guarantees.
Convergence guarantees.
Yeah.
Meaning,
Meaning it's not just a heuristic hack that happens to work sometimes. There's a strong theoretical foundation proving that, given enough time and data, the learning process will reliably improve and converge towards finding optimal solutions. Like, that's really important for trusting it in critical real-world applications.
right, you need that reliability. Okay, one last detail on the tests, just so we can picture it. Those small tweaks the AI was trying in the delivery problem, what kinds of moves was it actually allowed to make?
Good question. It could try specific, defined maneuvers, things like swapping the order of 2 stops on one truck's route, or moving a single delivery from its current spot to a completely different position in the sequence, maybe earlier or later. Or even flipping a segment of the route, taking a series of stops, say stops 5, 6, and 7, and reversing their order to 7, 6, 5. The key constraint, though, was that for any tweak it considered, it had to immediately check if the resulting plan still met all the rules. Did it violate truck capacity? Did it break any time windows? Only valid tweaks were explored further.
Got it. Okay, so let's zoom out from the tech details now. Why does this specific research, this Smart Explorer, why does it matter to you listening right now? How does it connect to everyday life?
Well, because this kind of technology has the potential to directly impact things you experience daily, mainly by making deliveries faster and cheaper. Logistics moving stuff around is a huge cost for companies. If they can optimize their routes and schedules this dramatically, they save enormous amounts on fuel, driver time, vehicle wear and tear. And hopefully at least some of those savings could filter down to you, the consumer, through potentially lower prices or maybe cheaper shipping options.
Exactly. And think about the flip side of the frustrations. Delayed packages, cold pizza.
Right.
This tech could mean your food arriving hot more often because the dynamic routing adapted better to traffic or demand. Or your package is showing up exactly when they said they would, much more reliably, less waiting around.
And it's definitely not limited to just delivery trucks and packages. Any industry that involves juggling complex schedules, limited resources, and strict rules could potentially benefit. The source specifically mentions applications like hospitals scheduling surgeries more efficiently, a super complex task with huge consequences,
Oh, yeah.
or optimizing the intricate plans needed for organizing large events, or even dynamically managing traffic flow across an entire city network in real time based on current conditions.
Okay, it sounds incredibly promising, potentially transformative for a lot of industries. Is there a catch? Any downside or limitation they mentioned right now?
Well, as with any cutting-edge research like this, the source does acknowledge it's not perfect yet. It's still relatively new.
And what was one of the main challenges they pointed out in getting it to work?
One thing they noted was that getting this innovative search layer to integrate and learn effectively within the neural network required some serious, quote, tinkering with the AI's inner workings.
So not quite plug and play yet.
Probably not for every single problem type, no. That level of deep technical adjustment isn't always straightforward. It might require significant expertise to adapt and fine-tune it for entirely new kinds of scheduling or routing problems beyond what they tested.
But presumably they're already thinking about how to make it even better, right?
Oh, absolutely. They mentioned they're already looking at ways to evolve the Smart Explorer concept. Things like enabling it to make smarter shortcuts or explore bigger, more complex changes to the plan, not just those small local tweaks. The idea is to help it solve even larger and more intricate problems even faster in the future.
Okay, so wrapping this up then. The bottom line here seems to be that DeepMind is giving AI a really crucial upgrade. It's moving beyond just recognizing patterns to giving it actual street smarts for dealing with these complex, messy, rule-bound planning problems that really mirror the real world.
Exactly. It directly addresses a core limitation that has, until now, kind of held AI back from truly optimizing many fundamental operations in business and society. It unlocks a new level of practical problem solving.
Which I guess brings us right back to that provocative thought, that question raised in the source material.
Mm.
Is this how it starts? AI mastering delivery routes today, could it be helping to decide much more complex things like who gets scheduled for critical healthcare procedures tomorrow?
It's certainly a very significant step in AI's ability to handle constrained, complex decision-making. And it definitely raises those important questions about the broader potential applications and, yeah, the implications as this kind of technology gets more powerful and widespread.